In this video, we'll be doing a proof on finding the electric field due to an infinite sheet using Gauss's law. Okay, so we have an infinite sheet, and let's imagine that this sheet will expand infinitely long, always. So the field will be going up like this and down. And the reason why this is an infinite field or infinite surface is because when you reach the end, let's say the end is over here, the field will point out like that. So we don't want that because for a Gaussian surface, the most ideal way to solve it without using calculus is to have a uniform field that's parallel and perpendicular. So to find the electric field, we start with Gauss's law. So the surface area integral E dot product dA is equal to Q enclosed over epsilon naught. Okay, so this is a Gauss's law formula. So what is the first step? Okay, so it needs to find the sum of the area. The sum of the area for the cylinder is the long part and the ends. So the cylinder plus two ends. So let's write that to the side. So we got this area for the cylinder. So like the long part, E dot dA plus the integral for the two ends, E dot dA is equal to the Q enclosed over epsilon naught. Okay. So from right here, we can cross out the E of the cylinder, or at least the long body part, because right here, if you look at the cylinder from the top down view, this is what it looks like. So here's the cylinder, and here is the sheet, the infinite sheet. The body, the charge on the body is pointing radially out, but the sheet is pointing upwards. So it's like the sheet is pointing out, but the cylinder is pointing like this. So they are perpendicular. But so if you take the phi of 90, like cosine phi 90, so cosine phi of 90, so cosine 90 is equal to 0. So the area over here is equal to the area of the cylinder is equal to 0. But if you look at the ends, like the circular ends, so this is a body cylinder and these are the ends, the charge is pointing up. So it's pointing parallel. So cosine is equal to cosine phi is equal to 0, which is equal to 1. So this is good. Okay, so that leaves us with the integral of the two ends, electric field dA is equal to Q enclosed over epsilon naught. Okay, so the dot product we can take out because this is parallel. The charge is parallel to the to the surface. So dot product is gone. And the two ends, since the charge is up here and down here, and we're looking for the total electric field, it'll be just multiplied by 2. So the integral of the two integrals of E dA is equal to Q enclosed over epsilon naught. Okay, finding Q enclosed. What is that? So Q enclosed is an area. So it's basically like everything that's within the surface. So there's three ways how we like there's three different Q enclosed that we can find. There is lambda, sigma, and rho. So all these are different, but we're looking for sigma, which is for area. So lambda is for line, sigma is for area, and rho is for volume. So we're not using a line or a volume right now. So we're focusing on the area, the area of the ends of the cylinder. And it would change if we're looking from a different perspective. Like if we're looking at an actual cylinder instead of just the ends. So to set it equal to Q, quick little algebra steps. Q is equal to sigma area. And area is pi r squared. Okay, so rewriting this to integral e dA. Forgot e. Okay, it's equal to sigma pi r squared over epsilon naught. Okay, so E and dA. E is a constant that we're looking for. So since it's a constant, it can go out to outside the integral. And dA, the integral and derivative of A is just A. So 2EA is the integral of 2 integral E dA is equal to sigma pi r squared over epsilon naught. Okay. So A, area with the two ends, is also pi r squared. So substituting that, you get 2 pi r squared E is equal to sigma pi r squared over epsilon naught. So your answer for the electric field would be sigma pi r squared over epsilon naught over 2 pi r squared. And this can be simplified by canceling out the pi r squared, leaving you with E equals epsilon sigma 2 over 2 epsilon naught. And this is really useful because you don't need to use any calculus to solve for a Gaussian surface.